Okay, so welcome back. And this time we're going to take a look at the Nernst equation, which is I guess probably the most common electrochem equation out there. It allows you to take a look at the actual cell potential that's going to result when your conditions are not standard. So either temperature's been adjusted or you have conditions that are not necessarily 1 molar for your solutions. However, sometimes it may be that your temperature is standard temperature, it's just that your solution concentrations are not standard, they're not 1 molar. And so this is an adjusted Nernst equation that allows you to work with standard temperature. This is the Nernst equation that you would utilize if your temperature is not standard. A couple things to be aware of. Please remember to group your Q calculation. Also, remember to keep this denominator grouped together. So in other words, what I mean by that is make sure that you have it in parentheses. Not as big a deal here when it comes to the adjusted Nernst equation, but never hurts to keep things in mind. So let's go ahead and take a look at this first example problem. What is the cell potential for a concentration cell made from cadmium concentration being 0.500 molar and a zinc concentration being 1.2 molar at 25 degrees Celsius? Well, if you watch the video on qualitative determinations, we've adjusted two concentrations away from 1 molar. In one case we've decreased and in one case we've increased. So this could either have the effect of really increasing our cell potential or really decreasing our cell potential. We need to know what's going to be where. So as we're looking at this, we're thinking to ourselves, we've got two half reactions to choose from. We've got cadmium 2 plus 2 electrons yields cadmium solid having a standard cell potential equal to negative 0.40 volts. Zinc's half reaction, reduction half reaction that is, forming the zinc solid, has a standard cell potential of negative 0.76 volts. So the one that we want to flip is always the one that's more negative or less positive, however you want to put it. In this case, more negative probably works out for us. And so what that tells us is that this half reaction is going to get flipped, changing the information into zinc solid yields zinc 2 plus and 2 electrons, giving us a standard cell potential of positive 0.76 volts. So when we're all done, we're really going to be looking at a balanced equation that looks an awful lot like zinc solid plus cadmium 2 plus yields cadmium solid plus zinc 2 plus, and it's going to have a standard cell potential that looks an awful lot like 0.36 volts, and that's definitely positive. So this is really helpful for us because, as you'll recall, these two equations both have Q associated with them. Now, in this case, we're given 25 degrees Celsius, which means that we're going to be able to utilize this equation right now. So with that in mind, we can start thinking about, okay, we're going to have cell potential equal to standard cell potential minus 0.0591 over N times the log of quantity Q. So it's time to start filling in what we know. Standard cell potential appears to be 0.36. We're going to take away 0.0591 over N. N still stands for the moles of electrons that are going to be transferred, and as we saw when the equation was balanced, that's a 2. So 0.0591, 2. And then we're going to multiply that times the log of, in this case, concentration for the product, so zinc's concentration, 1.20 molar, over concentration for cadmium, our reactant, 0.500 molar. And we got to keep that grouped together. And so let's see what we can spit out here in terms of a result for this. So 0.36 minus, and just for good measure I'm going to group all this together, so 0.0591 divided by 2 times the log of the quantity 1.20 divided by 0.500, and we end up with a value. Got a lot of decimal places here. I think I'm going to stick with, in this case, I'm looking at my concentrations. I had 3 sig figs there, so I'm going to stick with that. And we're talking about a value of 0.349 volts. And that's definitely a positive value. So we've got that particular one worked out. Please remember, just because you're given the concentrations doesn't mean that the first one's on top or on bottom or anything like that. You've really got to take a look and see how the balanced equation is going to arrange itself so that you can properly put your ion concentrations in the correct locations for your Q calculation. So we've got another example problem that we can work right here. Same issues are going to persist. So we've got chromium 3 plus 3 electrons goes to chromium solid. Cell potential on that one's going to be, looks like it's going to be negative 0.74 volts. And in the case of calcium, we got Ca2 plus 2 electrons goes to calcium solid. And cell potential on that one's going to be, and we've seen this before, negative 2.87 volts. So once again, we want to flip the half reaction. That's going to be more negative, and it looks like that's going to be our calcium half reaction. So that goes away. We've got calcium solid goes to calcium 2 plus 2 electrons. Cell potential on that is now going to become a positive 2.87 volts. And so our balanced equation looks an awful lot like calcium solid plus Cr3 plus yields chromium solid plus Ca2 plus. But I'm sure you're thinking the same thing that I am right now. Somebody jumped the gun. Our electrons weren't balanced, so I can't go ahead and start adding up the equations until my electrons are balanced, which means I need to put a 2 here, get a 6 there, and put a 2 here. I need to put a 3 here, I need to put a 3 there, and this needs to become a 6. So when I start dropping down my values, my balanced equation certainly looks much different than it did a moment ago. And what this does for me is it gives me the correct coefficients, which is going to certainly have an effect on the way that I'm calculating my Q value. It also then establishes the value for N, but thankfully it has very little effect on my calculation of the cell potential, for standard cell potential I should say, for the cell. And the standard cell potential is going to be 2.13 volts. So when it comes to it now, I can use the equation cell potential is equal to standard cell potential minus RT over NF times the quantity natural log of Q. So with that in mind, I can start making my replacements. I know standard cell potential is going to be 2.13. I've got an R value of 8.3145 because we're talking about energy. My temperature is going to be 353. And then don't forget to group these terms. It's 6 electrons being transferred times 96,485, and then the natural log of. And what I have noticed now is that I'm going to have my calcium ion concentration is going to be 0.370, and that's going to need to be cubed because of the coefficient 3. And that's going to be over my chromium concentration value, which is going to be 0.945. And that value is going to need to be squared because, again, of the coefficient there. And so it looks like my cell potential is going to be a value of 2.13 minus the quantity 8.3145 times 353 divided by, making sure I've got parentheses now, 6 times 96,485, close those parentheses, times the natural log of the quantity, and in this case I'll add additional parentheses just for good measure, 0.370 to the third, actually, yep, close that quantity, divided by quantity 0.945 to the second. Close that one up, make sure everything's grouped together. And it looks like I'm going to end up with just a slight increase to the cell potential here at a value of 2.14 volts. Again, keeping 2 sig figs here. And so that's pretty much how you're going to work with the official Nernst equation, which I would say here, as opposed to the adjusted Nernst equation, which we saw up here. So remember, this one only works at 25 degrees Celsius. The one that we saw here works at any temperature. So I hope this helps, and